Okay, calculus for dummies, like you, by your fourth favorite saxophonist, Tim. All right? So, chapter 0, a brief prologue to our magnificent journey, okay? I know you guys have some apprehensions about math. A lot of people hate it. I know. But we're going to be fine. It's all going to be good. I've taken a lot of the mental heavy lifting and I've done it all myself, and you're not going to have to actually understand any of that. The reason that you don't like math, all the numbers and the lack thereof, I've taken care of it all. It's all good. Okay? You're just going to, but you're going to know what all the main concepts represent, and you're going to be way smarter than everyone else that you know. Okay? So, chapter 1.1, we're going to start with functions, because everything is built off of functions. Okay? So what is a function? It's a system, okay? You have two variables, an input and an output, okay? And it does the same things to that input to get an output, okay? And then you get something that looks like a line or a bunch of lines. This function, x squared minus 4x plus 2, it doesn't fucking matter, right? That's the actual function, okay? So, they often look like continuous lines, right? It's all stringed together, okay? This is not a function, okay? Okay? One of the rules of a function, okay, is that every input has one output. Look, input on the x-axis, two outputs. You don't know which one you're going to... You're like, okay, I'm going to start with x equals 2, right? You don't know what you're going to get there. You could get whatever this is, or you could get whatever this is. That's not a function, okay? We deal with non-functions in calculus, but I'm not going to go over that, because you'd have to actually understand it on a slightly deeper level than I'm going to go through here. Okay. So, you might notice, a lot of them are very straightforward, right? You have one input, one output. It's very nice. We love these. Many such cases. But, okay? Chapter 1.2. The evil persnickety function variety. Okay? We don't like these. Okay, look at this disrespectful young man. Look, we can't solve the function at x equals negative 1. Try plugging that into here. You see, negative 1 plus 1, that's 0. You're dividing by 0. This is bad. You don't want to divide by 0. That's bullshit, okay? See, we don't... You have no idea what the function would equal there, right? So, what would a studious YN like yourself do in such a precarious predicament, okay? My speaker note says, come on, bro, put the fries in the bag. I don't know why. Okay, so, moving on to chapter 2. A brief introduction to the illustrious limit, right? Okay, so,
I didn't like these.
What does a limit do, right? We use limits when functions are bugging, all right? When they're tweaking. It allows us to make a prediction about what the function would be if it wasn't retarded. Okay, so.
Yeah.
It's like this, it's kind of like how, you know, when on a Tuesday morning, when you crash into a tree, right? You know that you're going to crash into the tree for a brief moment before you crash into the tree, because you know that you're headed towards the tree, right? It's kind of like that, but for math, right? So, what does it do? It lets us manipulate the function to get a function that looks the same, but is not disrespectful and says no to trying to solve it at certain points, right? So it's like a get out of jail free card. It lets us ignore certain rules about functions like extraneous values, which I'm not going to explain. So, all we have to do, in this case, factor it. See how I've done that all for you? The hard part of math, I did it all. You see how x plus 1? It's like, imagine if both sides were multiplied and divided by 5, they undo each other so you can get rid of them, right? And so, you get left with this function, right? And, because, again, they were being multiplied and divided by the same thing, they cancel each other out. You get a function that looks the same, but isn't retarded. And you can do that with other stuff. That it's not fun. See how I've done it all for you, right? Because I'm doing all the hard stuff for you. But there's a bunch of different processes you can do to achieve the same thing. They transform the function, and they make it look like a function that you can actually do stuff with. Okay, so here's how it's notated. This looks spooky. It's basically just saying, hey, what's the function look like it approaches, right? What's the output look like it's gonna be as the input approaches whatever value we want here, which is c, right? So, to solve it, all you do is take this number here and put it in for x. You see?
Yeah, I remember that.
X is 3. 3 squared, see? 3 goes into x, and you solve it. And when we get a weird division by 0, then the limit tells us, hey, you can ignore that the 3 doesn't work and just change the function until the 3 does work, right? Quick example right here. So, x approaches 2. Yeah. See? As x is approaching the 2 line, the y is approaching the 4 line. So the limit here is 4, right? So, chapter 2.2, continuity and limits. Okay, so I'm very sorry, guys. It doesn't work all the time. The limit doesn't work every time, okay? So, what is continuity? They have no breaks or holes in them, okay? The easy way to remember is if you could draw the function without picking up your pencil, there's a more complicated definition that we'll get into, but if you can draw the function without picking up your pencil, then you're all good. It's continuous. Okay, so this function right here, continuous?
Continuous.
That's continuous.
It's continuous.
Yeah.
Right? What about this one?
No.
The limit doesn't work on him. What about this?
No.
And what about this?
Continuous.
No!
Oh.
No! There's a hole there. You didn't see it. There's a hole there. You see? You just got trolled. Yeah, okay. So you see how this tiny hole that exists at one infinitely small point, it removes the continuity.
Okay.
It's stupid. It's also why technically the pencil thing doesn't work and we need
You
the more
can draw
complicated
that circle.
because some smartass would be like,
Yeah, that's
you
what I
can
was
just
gonna
draw
say.
this. No. Imagine it like a tiny little hole. Imagine if the circle was not a circle and it was 2 heavy circles that don't quite touch. So, when limits fail to exist.
Ooh.
I thought I was going to fall over.
That would
Okay,
be cool.
so.
Yeah.
We have 2 types of discontinuities, right? There's removable, where it's just the tiny little hole, and then there's non-removable, where it's slightly bigger. Actually, this function approaches infinity, opposite infinities on both sides, so the hole is infinitely wide. Not good. So, because a limit preserves the shape of a function, if you cannot reconcile this distance without changing how the function looks, then it's a non-removable discontinuity.
Oh!
Limit doesn't work here because even if you change the function to look like it, you can't. How would you do that? You can't fix that, okay? It's more broken than that goth girl that you think you want to date, right? So, the other case is this. I'm not even going to try it. It's called oscillating behavior. The function for this, I'm pretty sure, is the cosine of 1 over x or something. But you try to tell me what's going on here. What do you think's going on right there? You don't know, and the limit doesn't either. So, yeah, it doesn't work. Okay. Chapter 2.4. Proving that a function is continuous using limits. This is the more complicated definition. Okay. So this one's really simple. A function is continuous. That is not a typo. The 2 F's there, that is a mathematical term. If with 2 F's is an abbreviation for if and only if. That's in my speaker notes. If there is a limit at the point, right? So if the 2 things look like they're meeting, even if they aren't, if they look like they're meeting, you're good. If there is an actual point there, so no hole. So there's a limit and there's no hole, right? And the 2 are the same, okay? Because sometimes you can have a thing where they look like they're meeting, but then the actual point.
Yeah, I was thinking they 2 are equal.
They 2.
Or the 2.
So yes. Yeah, that's a typo.
Yes!
That's a typo. I'm sorry, guys. I was too cocky. Chapter 2.5. What is the point of all this? And the answer is simple. Limits are used to prove everything else. We use limits to define the other 2 things that I'm going to talk about during this presentation. By the way, we're a third of the way done already. So it's going to be faster than Conrad's.
Yeah.
We're 10 minutes in. Nothing, like I said, we're going to use limits to prove 2 more things. And neither of them are applicable if your function is not continuous.
Okay.
So you also need to understand continuity. So, chapter 3, an introduction to differential calculus. Chapter 3.1, the slope of a line. Okay, look at this. Look at this line, okay? You know how to calculate. You've all taken Algebra 1. It's rise over run, right? This one goes up 4 and goes across 2. Goes up 2, goes across 1, right? So the slope is 2, because it's up 2 over 1 across. Yeah, blah, 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 right? So, easy. The slope formula. Sounds scary, right? This is just saying you have 2 points. You subtract the difference in their height, and you subtract the difference in their horizontal distance from each other, and you divide them, and you get the slope. It's really easy, right? So, tell me the slope of that line.
No.
Okay, so sorry, hang on.
Weird,
It would
right?
be
have a slope. It doesn't have one slope, right? It's got a
Yeah.
different. It doesn't even have a. There's no straight lines in here. It's all curvy worvy, right?
Yeah,
It's weird. You don't want that, okay? So, how can we ever reconcile this, right? Chapter 3.2, finding the slope of one
We
point.
can ask
Okay,
a question,
now,
Ben.
you're thinking, right? The slope of a single point, yes, okay? Because you're like, wait, the slope formula requires that we have two different points. What the hell's up with that, right? And so we're going to use the context around that point, right? Like what the slope looks like it would be based on, the points around it, right? So let's just pick a point. We're going to call it C, okay? Keep in mind, x value is 2 here, right? So that's C, right? We pick a second point, x, right? And also the function we're using is just regular x squared, right? Easy, easy. So we've got 2 points. We're going to make it 1 point. But how? Well, okay, first of all, f of x is the same as saying y. So this is just translating the slope formula into terms here, right? So, now, as x approaches c, the limit, right? Because if x is approaching c, then that means they're going to become the same point, right? Because it's approaching the other point. It's right up in there. So that's weird, right? Because if you plug in x for c like I told you to do, you'll get this, which is 0 over 0. Now I didn't tell you this, but we like 0 over 0. 0 over 0 is good, okay? Because 0 over 0 means that we can cancel stuff out, okay? So this is the math. You don't even really have to think about it. See, again, I did it all for you, okay? But remember, I told you that the function was x squared and that our c point was 2? That mattered because now you can plug it into the limit and you can do all this. And you see, we can factor because it's 0 over 0. We know we can factor because it's 0 over 0. And you get this, and you get 4, which means that our slope at that point is 4. Right? So, right here, slope's 4. If you pick a line with 4 and you make sure that it passes through at this point, you see, it looks like it's about that slope right there. Yeah, you see? It's not like going haywire perpendicular to it. It's 4. It's really nice. You like that, right? So, chapter 3.3, the actual derivative. We calculated the slope at a point. Now I'm going to show you what the derivative is. So what is the derivative? It's a function that gives the slope of every single point. It's a shortcut. It does what we just did a million times over in a fraction of a second. It's really cool, right? So like here, the slope here is positive. You see how we have a positive point? The slope here, even though the function's negative, the slope is going up. It's positive, which means that our derivative function plots it as a positive point. See how the slope here is 0, so our derivative touches the x-axis, right? So, how do we find the derivative? Well, now we're going to pick a point x, right? So here it's x equals 2. Our function is x cubed this time. It's a little different. We pick a second point, and we're not going to give the point a symbol. It's going to be x plus h, so that the distance between these two is h. Yeah?
Yeah.
Does that track? Now, we put all that into this formula, right? See, f of x plus h is our point, so this is just the height at that point, right? And then we have x plus h as our point, and then our other point is x, right? Now, you might notice that we have an x and a minus x, and they get rid of each other, and now we have an even simpler formula. F of x plus h minus f of x over h, right? Now, bear in mind, h is the distance between them, so if we want to bring the points together like we did with the last one, we take the limit as h approaches 0. Are you seeing any problems with this?
Because there's a 0 on the bottom.
You don't want to divide by 0. Yeah. But, math time. If we just stick x cubed in here, right? And we just x plus h, because x plus h goes into x, right? This is what we get out, 3x squared, which means that the derivative of that function is 3x squared.
Oh.
So, basically, if you want to find the slope of the x cubed function, you take the x value of the point that you're trying to find the slope for, plug it into 3x squared, and whatever you get out is the slope.
Like 3x squared or?
Right.
Oh yeah, 3x squared, okay.
Chapter 3.4, the shortcuts. Okay, we can all agree that took forever. That was a lot of work just to find the derivative of one function. You know how many derivatives I've had to find? It is probably a 4-digit number, right? So, there are 2 commonly accepted ways of notating a derivative. I'm just getting this out of the way. Okay, calculus, weird because it was invented by like 4 different people in 4 different countries at the same time, and they all had their own way of writing stuff. So a few of them survived. There's others that like we know about that we don't use because they're stupid and clunky. But these are the 2 that they'll teach in basic entry-level calculus. The derivative has a little apostrophe there. It's f prime of x. Or you can just say dy over dx, right? That's the difference in y over the difference in x, right? y2 minus y1 is the difference. It's slope. It's the slope formula. And you treat it like an operator. You apply it to x cubed, and you get this as your output, right? It's like timesing it by something, right? And with that, all the shortcuts.
Hey.
I have all of these committed to memory.
Let me screen.
Okay, I have like a knee-jerk reaction where I can just, if you threw any of these at me, I'd just be like, okay, I know all these. It took a lot of study.
TJ, look over here. What is arcsine of x?
1 over the square root of 1 minus x squared.
Well,
What about UV?
UV?
Yeah.
U prime v minus UV prime.
It says plus.
Oh, plus.
what is bx? Or b
bx?
squared x.
B to the x?
Yeah, b to
It's
the
b
x.
to the x times the natural log of b.
That's right.
Okay, anyways, sorry, I got the minus one there. That's my bad. If I was writing it down on paper, I'd get it.
Right,
Anyways,
of course.
This last one is called the chain rule. It's like the most important one, but I'm not explaining it, and I'm 73% sure that we can get through the rest of this stuff without going into this, you buffoons.
Right.
Chapter 4, an introduction to integral calculus. Look at that. You've made it through 2 of the 3 major concepts, and I'm guessing that you're still somewhat tracking what's going on here, right? So that's good for you, right?
No.
So, can you find the area of this rectangle?
No.
Well, we don't.
Base times height, yeah?
Well, yeah,
No, we
but
don't
we
What
don't have the
about
numbers.
the triangle
What is
here?
that?
You can't see it super well.
But-
Base times height
No,
divided by
but-
2, right? It's really easy. You're not taking a math class. You probably failed the last one you took.
I didn't fail it.
Bro, when we were sophomores, I literally heard our teacher telling you she was going to force you to drop the math and go to the next lower level.
Bro.
Yeah, but
Okay, circle. Easy, right?
I know, we
Pi
do that.
squared. You all know that? Yeah. Okay. How about that? You find the area of that? Can you do that? Can you do that?
Looks a
Can you
little.
find that
Looks a
area?
little weird.
No, it's a weird shape. That's what we use integrals for, amongst other things. Okay, so chapter 4.1, the Riemann sum. Okay, so instead of finding the area, let's estimate it. I've actually already explained this to Ben, so how would you estimate this area? Let's fill it up with rectangles, right? So we got some rectangles here. Right?
Ah.
We know how to find the area of rectangles, just remember them. Base times height, base times height, base times height. Yeah, okay. So we're gonna notate it like this. Okay, this looks scary.
Yeah.
It's not, okay? The number on top. Okay, let's start with the scary one. That's a capital sigma. Sigma.
Wait, I don't know about that in yeah.
It means summation.
Yeah,
It is a
yeah.
fancy plus sign,
I don't know
okay?
about that one.
6, that's the number of rectangles, okay? I equals 5. 5 is just, that's the horizontal distance. Look, see, we're going from 1 to 5. The width of the base here is 5, okay? So I equals 5, okay? X sub 1, okay? This is just the starting value, okay? By the way, f of x, that's the height of the rectangle. Delta x, delta means the
Yeah,
tangent,
yeah.
okay? It's the distance, it's the base. So this is base times height, 6 times over this interval.
That
See,
makes sense.
that's not that bad. So this is the general formula, right? We just got rid of the numbers. It's fine. Because when you actually use it, you'll plug all the numbers in and you'll get the last thing you saw, right? So simple. Chapter 4.2, creating the integral. Okay, so as you can see here, the more rectangles you have, the more accurate you get. See how there's a lot of white space there, a lot of area we're not accounting for? Less area. Less area, less area. The more rectangles you get, the more accurate, right? So you want infinity rectangles. So remember, n is our number of rectangles? Take the limit as n approaches infinity. And boom. Because you have infinitely many rectangles, which I know doesn't make sense because then they'd have an infinitely thin base and the theoretical area is 0. It's okay, we're mathematicians, we don't care. So that's our perfect approximation. And because we calculate the width of the rectangle by dividing this by this. Dividing it by infinity would get you the width of 0. It's dumb. So instead we just ignore our problems, just like me with my marriage, right? And rewrite it as this fancy squiggly that you see in like the Oppenheimer movie or something.
I
right?
see that, yeah.
That is a fancy. That is the letter S. That is saying sum, add. Okay, it's the same thing. I'm dead ass. That is supposed to be a fancy letter S.
So that's supposed to be sigma, like adding. Is that kind of similar to that?
Yeah, it's
Okay.
the same thing except it's like, hey, we're doing it precise, right?
Oh.
So,
Huh.
you did it. That's it. You made it through calculus. I could go deeper on. I could make a presentation 3, 4, 5 times longer than this just on integrals. That goes deep, and there's a ton of applications and deeper stuff that I didn't go over. Okay, like Conrad with the Warhammer lore, right?
Yeah.
It's studious. But you gotta understand. By my estimate, you now have more calculus knowledge than about 90% of the American population. You don't have more calculus knowledge than any of the Asian population. I'm sorry,
Right.
but I might.
Yeah.
Chapter 5. A closing statement.
Well, yeah.
What's the point, right? You're sitting there, this is the age-old question that you see every snarky kid who thinks they're onto something ask in movies. Excuse me, Mr. Whatever your last name is. When are we ever going to use
Mr.
any of
White.
this? Calculus is actually really important and really applicable. So here's some uses of calculus. Optimizing how resources are used in construction. Making multivariable economic models factoring in complex interest rates. I just got done with that a couple of weeks ago. Right? Calculating chemical reaction rates so your car engine doesn't explode. Finding complex areas and volumes, like I talked about. Determining centers of mass in objects and moving systems. That's just something I've done in my engineering classes. Right? Relating positions, velocities, and accelerations. Relating moving objects to one another. You got 2 objects moving, you want to know the distance between them is changing? That's important for stuff, right? Estimating how much time things are going to take, If you're filling up a lake and there's water evaporating while you're filling it up, and it's like the water evaporates more when there's more water in the lake and stuff like that, right? You want to know, right? When are you going to be done? What's the most water you can put in there, right? This is used for making graphics and animations for computers and games. Designing precise acoustics for musical instruments and performance halls, okay? We talk about that in our band class, right? Medical imaging of processes and machines, Ben had like an MRI literally yesterday or something, right? Pretty much every single invention involving motion, engines, electricity, anything, okay? All of it uses calculus. Speaking of electricity, calculating electric fields so your house's power system doesn't fry itself and you along with it. The same can probably be applied for like submarine sonar systems, right? Explaining how these diseases are going to spread in the world, right? Making statistical predictions about quantum particle locations, right? Like that new Microsoft chip uses quantum whatever the hell. I think they might have just thrown the quantum in there as a marketing term. I think it's just a post.
What does what does quantum even mean?
Quantum means really
Okay.
small.
Yeah.
So quantum physics is just the study of basically subatomic particle behavior. It's not as
Quantum.
To do with the
Movies never use that term right. Creating shipping and airplane routes because you want to follow the jet streams, you want to follow the currents. Those aren't just like rigid things, they're changing, they're amorphous, right? Making weather forecasting predictions and all that. Okay, do I really need to go on? It's pretty important.
I get it.
That said, thank you for your time and attention. In 25 minutes, I've just explained calculus to you. I'm pretty proud of myself.
It's
I'm
actually-
proud of you for hearing me out.
It's
'cause
actually
I
been
know a
like
lot of
24
people
minutes.
are really, look, my thing says 25 minutes.
Okay. No, I'm just kidding.
I have a timer going on here.
I thought you
And
were
my
gonna-
voice is really dead, and this presentation is like 40% the length of Ben's, which I will be telling my family because they scoffed at me when I said this thing had 100 slides. Okay, yeah.
I
All
thought
right.
you were gonna
Thank
make out a
you.
worksheet.
All right,
There you go.
thank
Now
you.
you guys know calculus. Hopefully
Hey.
you're slightly